y'all, today we're going to be talking about section 7.2, which is about photochemical smog. The learning objective for today is that you can explain the causes and effects of photochemical smog and methods to reduce it. Some of the essential knowledge that you're going to gain is how photochemical smog is formed, some of the environmental factors that affect its formation, the times of day when it peaks and why this is, how volatile organic compounds are going to impact it, areas where it's going to be predominant, ways that we can reduce it, why it's harmful. There's going to be a lot of stuff that you're learning today from these notes. All right, so we're first going to talk about photochemical smog precursors, basically the ingredients to it and the conditions that form it. And just to start out so that you know what photochemical smog is, it's basically just meaning smog that is related to light and chemicals. So the chemical and photochemical, and then the photo means light. So we're getting like sunlight plus chemicals is creating this smog. So the name kind of tells you what it is, but I just wanted to break that down before going into the notes. All right, so the precursors, which again are basically like the ingredients. The first thing that we have to start with is going to be nitrogen dioxide. And the sunlight is actually going to end up breaking up the nitrogen dioxide into nitrous oxide and then a single oxygen atom. Now this free oxygen atom is going to combine with oxygen gas to create ozone. But the precursor, we have to start with nitrogen dioxide. Another ingredient that we have to have is going to be VOX. And VOX stand for volatile organic compounds, which is just kind of a big catch-all term for a bunch of these hydrocarbons that have the ability to bind with nitrous oxide and form photochemical oxidants. So it's kind of like a big catch-all phrase for them, and you don't need to know like every single individual one. We're just going to call them VOX here. And some of the basic tendencies of VOX is that they're carbon-based compounds that volatilize, which means they evaporate easily. That's where the volatile comes from. So an example you can think of is like nail polish remover. If you've ever spilled nail polish remover, you know that it evaporates very quickly, and that's because it's a VOX. So that volatile aspect of it makes it evaporate really quickly. Now, some of the sources of VOX, they can come from a lot of places here on Earth. You can get them from gasoline, formaldehyde, cleaning fluids, oil-based paints. Even some coniferous trees are going to have VOX that they release, and that's actually what gives trees their pine smell. And then the third thing, because we have that nitrogen dioxide, when it's split, the free oxygen is going to combine with oxygen in the atmosphere, which is going to give us ozone from that free oxygen binding with the oxygen gas. It forms O3, which is ozone. Now, you may remember from our levels of Earth's atmosphere that ozone is naturally found in the stratosphere, and it is used to kind of help actually protect us. Ozone is great for us when it's in the stratosphere. However, because of all these precursors and things that we are doing, we actually end up forming it in the troposphere. And the problem is when it's in the troposphere at Earth's surface where we're found, it actually is a respiratory irritant. So it's good in the stratosphere. It causes respiratory irritation when it gets lower than that. Additionally, it's also damaging to plant stomata. And it's going to limit growth because the plant stomata, remember that's the little holes in the plant's leaves. That's how they breathe in carbon dioxide. It's how they breathe out oxygen. So when you're damaging that, it's going to impact the growth of plants. Now, some of the conditions that are required in order to create this photochemical smog. The first one is going to be sunlight. Remember the photo part of photochemical, and the sunlight is what's going to drive the ozone formation because sunlight is what breaks down the nitrogen dioxide into NO and a single oxygen atom, and that free oxygen atom is what's going to be resulting in the O3 being formed. Additionally, warmth. Hotter atmospheric temperatures are going to speed up this ozone formation. It's going to cause the VOX to evaporate more, and thus it's going to cause more smog formation. So like in the summertime where we have more sunlight and more warmth, that's where we're going to be getting even more of this photochemical fog being formed. So in order to understand the photochemical smog and how that is formed, we actually need to look at the normal ozone formation that we typically see because of human impacts. Now, first we're going to get our morning commute is going to lead to higher nitrogen dioxide levels from car exhaust. Remember that gasoline and this exhaust is going to give us a lot of our NO2. So we're going to have a lot of NO2 into the atmosphere. Then after the morning, you've got the sun rising. The sun is going to come in and going to break that nitrogen dioxide into NO and O. So we're going to get nitrous oxide and a single oxygen atom. Now, within the atmosphere, we have oxygen gas floating around. That oxygen gas is going to bind to this free oxygen atom because this free oxygen atom is not very stable, so it's going to want to bond with something pretty quickly. So this oxygen atom is going to bond with the oxygen gas that we have in our atmosphere, and that is going to be what forms ozone, which is O3. Now, typically we're going to see ozone formation peaking in the afternoon when sunlight is most direct and we've had a lot of that nitrogen dioxide emission making its way up into the atmosphere after our morning traffic has kind of peaked and now we got warmth. And so we're going to see in the afternoon is where we actually get a spike in this ozone formation. Now, under these normal conditions, what we're typically going to see at night, ozone is once again going to react with nitrous oxide. And it's actually going to kind of reverse this equation that we just talked about because we don't have the sunlight anymore. And now all of a sudden we're going to have this nitrous oxide. It's going to be forming nitrogen dioxide and the oxygen gas. So under normal conditions, this ozone is going to be formed in the middle of the day mostly. But then at nighttime when the sunlight's gone, we kind of have it reverse. And so by the end of the night, the ozone levels are going to be dropping and it's going to be kind of this cycle that ultimately is going to kind of be reversing itself when the sun goes away. Now, these are under normal conditions. So now we're going to talk about the photochemical smog formation. So the first three steps are going to be the same as the last one, so I'm just going to kind of go through them quickly. So you've got your morning commute. You're going to have more nitrogen dioxide in the atmosphere. Sunlight's going to break it apart. That broken apart oxygen atom is now going to bond to form ozone. We're going to get ozone in the atmosphere. But here is where we now get a disruption to this in the formation of photochemical smog. Now, because of all the different things that I mentioned, such as like gasoline, cleaners, cleaning solutions that are used at laundromats, that's where we're going to get these VOCs. VOCs are now going to come in and bond with the nitrous oxide, and they're going to form what's known as photochemical oxidants. Now, photochemical oxidants, it's again just kind of a catch-all term. You don't need to know every little chemical symbol for them. Just know that VOCs combined with nitrous oxide is what makes our photochemical oxidants. Now, the problem is now that this nitrous oxide is bonded to, it's created other chemicals. So we don't have this nitrous oxide just floating around anymore. So we don't have it able to go and react when the sun goes down. So this typical thing that we were just seeing in our last slide where we reverse the equation because the nitrous oxide is going to come and pull an oxygen and we're going to go back to our nitrogen dioxide and our oxygen gas. That doesn't happen because the molecules in the nitrous oxide are now bonded with other things in the photochemical oxidants, which means ozone's going to continue building up instead of returning back to that nitrogen dioxide and the oxygen levels overnight. So we're just going to have a lot of ozone building up. As ozone's going to be building up, this is going to be forming the photochemical smog because the ozone is now going to combine with these photochemical oxidants, and that's going to form this photochemical smog. So This process is not one that's easily being reversed just by the sun going away at night, because we're having these levels build up. And so this is what's going to be giving us our photochemical smog. Now, here's going to be some factors that increase the smog formation. So as we talked about, increasing vehicle traffic, that's going to increase the nitrogen dioxide emissions and therefore the ozone formation. So increased vehicle traffic is something that can increase smog formation. The more VOC emissions that we have from gas stations and laundromats and plastic factories and all of those. So the more vehicle traffic, the more ozone we get. The more VOC emissions, the more of these photochemical oxidants we're going to be having formed, and the photochemical smog, which comes from it. More sunlight, which happens in the summer and the afternoon, also leads to more ozone. And then warmer temperatures are going to be speeding up the evaporation of the VOCs and the reactions that lead to that ozone. So what we actually end up seeing is urban areas are going to have much higher levels of this photochemical smog, because all these factors are going to be happening a lot in urban areas. In urban areas, we have more traffic, which means you're going to end up with more nitrogen dioxide. We have hotter temperatures because of the low albedo of blacktop and the cement and the buildings. It's going to be having hotter temperatures from all of these. You're also going to have more VOCs because there's more gas stations and more factories in a compacted area in urban areas. You're also going to have more electricity demand. And so you're going to have more of those NOx emissions from nearby power plants in order to supply more of the people. So in urban areas, we're getting a lot more of this photochemical smog formation because all these factors are occurring in urban areas. So we're going to look at some of the impacts of why this photochemical smog is not good. So for impacts, the first couple are going to be environmental. Now, an environmental problem is that it's going to reduce sunlight because this smog kind of blocks out the sunlight, which is going to limit photosynthesis. And as I talked about earlier, ozone damages plant stomata, and it also irritates the respiratory tracts of animals. Now, for humans, since we are kind of animals, we are going to be having our respiratory tracts also damaged from this ozone. And it's also going to worsen asthma, bronchitis, COPD. It's also just going to cause irritation in the eyes for humans. And then some economic impacts. You're going to end up having increased health costs due to having to treat that asthma and bronchitis and COPD. You're going to have lost productivity due to sick workers missing work or dying from the COPD or asthma. And then you're also going to get decreased agricultural yields due to the fact that we have less sunlight reaching the crops and we're damaging the plant stomata. So all of these are going to be impacts of having more of this photochemical smog formation. So what are some things that we can do to reduce it? Now, first of all, it's going to be decreasing the number of vehicles on the road. This is going to decrease the nitrogen dioxide emissions. The less vehicles we have, the less gasoline is also going to mean fewer of those VOCs. So doing things like carpooling, taking public transportation, biking, walking, working from home, all of those are going to lead to a reduction in the vehicles and the gasoline that we're using. Additionally, for energy, having increased electricity production from renewable sources that don't emit NOx, such as solar, wind, and hydropower, or also having natural gas power plants release as a form of energy, because natural gas power plants release far less NOx than coal do. So these are going to be some ways that we could reduce the amount of photochemical smog that we're going to be getting. All right, so this is going to be your practice FRQ for 7.2, where you're going to practice the suggested skill of describing the relationships among variables and data represented. So I want you to look at this graph here. That's going to show you a few different levels of air pollutants. And I want you to explain the relationship between nitrogen dioxide concentrations and ozone concentrations represented in this graph. Now, pay attention to the fact that it says explain, not just describe. So you're going to talk about this relationship, and you're also going to give a little bit of a background to why this relationship exists. So that'll be your practice FRQ for 7.2, and those are your notes on 7.2 about photochemical smog.